Es un verdadero honor estar hoy aquí en Puebla, en México. Debo agradecer a los organizadores el que me hayan invitado hoy a dar esta charla plenaria. Y tengo que empezar mi charla pidiendo disculpas. Como ha dicho Abraham, llevo 43 años viviendo en los Estados Unidos y mi formación científica y técnica ha sido en los Estados Unidos. Y desgraciadamente es un poco una vergüenza, pero hay mucha terminología técnica, sobre todo del tema que les voy a hablar hoy, que no la sé muy bien en español. Y a riesgo de hablarles a ustedes en Spanglish, que va a ser una ofensa a nuestro idioma, pues voy a darle la lección en inglés, que sé que todos ustedes van a entender muy bien. Y durante el turno de preguntas, pues me podrán hacer ustedes las preguntas en español si quieren, o en inglés, como ustedes les parezca. Entonces, si ustedes me permiten, vamos a dar la lección en inglés. So today what I would like is to talk about the motion of the cerebrospinal fluid and the role that this fluid plays in various important disease processes in the central nervous system. Because I imagine that most of you do not have formal training in medicine, I'm going to begin my talk by giving you a very brief and simple introduction of some of the relevant physiological and anatomical considerations concerning this flow, so that then you can follow the rest of the presentation. And then the vast majority of the talk will be dedicated to two specific problems. One is the circulation of this cerebrospinal fluid in the spinal canal. And this is a very important process and a very important problem, because today, because there is what is called the brain-blood barrier, chemotherapy cannot be given to the brain because it cannot cross from the blood into the brain parenchyma. And a way in which this is done to bypass that barrier is by injecting directly the chemotherapy in the lumbar region, in the back, into this fluid, into this cerebrospinal fluid. So the motion of this fluid around the central nervous system then determine how this chemotherapy is delivered to the system. So that's a very important problem. And the second problem is what is called idiopathic normal pressure hydrocephalus. This is a problem that, as you're going to see through the talk, leads to dementia, and it's a problem of the adult population. Typically occurs in individuals over 70 years of age. And what is very important, and has been our motivation, is that it's the only reversible form of dementia. As you know, there are many forms of dementia, for example, Alzheimer's diseases and so on, which we do not have currently a solution or a treatment for it. But this one, if it is diagnosed early, then, as you're going to see, it can be reversed, so it can be treated. So let's begin with the first, this very simple introductory thing. So the cerebrospinal fluid is a clear fluid that bathes the entire central nervous system. The central nervous system is composed of the brain and then the spinal canal. En español se llama líquido cefalo-raquídeo. Cefalo porque riega el cerebro y raquídeo porque está en el canal raquídeo, lo que en inglés llamamos spinal canal. And it's generated from the blood plasma. So it's very similar to plasma. In other words, it's similar to water. For everything that you need to know and to understand this talk, you should think of this fluid as a fluid that is Newtonian fluid and has viscosity and density that are very similar to water. Okay? That's why, for example, the second problem that I'm going to describe for you is called hydrocephalus. And as you know very well, hydro means water, right? So it's water in the brain. So this cerebrospinal fluid plays a dual function. The first function is because it's surrounding the entire brain and the spinal canal. It acts like a shock absorber. So when you hit your head, right, you have this fluid that is surrounding the brain and is between the brain and the ridge of the skull, and that acts as that shock absorber to protect the brain from the trauma. So that's one important function. The other important function is the brain of any one of you here, adults, it weighs probably about 1.5 kilos. And because it's bathed by this fluid that has the density of water, and the density of the brain is slightly lower than the density of water, the brain is actually floating into this fluid. So instead of exerting this weight of 1.5 kilos on the stem, right, at the beginning of your spinal cord, exert only an equivalent of about 50 grams. So that's another very important function, which is a physical function. But for the talk today, I would like you to pay attention to this very important role. The cerebrospinal fluid plays a very important function because it circulates nutrients and also removes the product of the waste product of metabolism from the central nervous system. So it's a fluid that has to circulate, has to move, because it's bringing fluid, it's bringing nutrients, and it's taking away the products of the metabolism. Here you have a cross-section of the head of an individual. So this is a mid plane. So the skull will be surrounding the brain. The brain is indicated here in yellow. And notice that the brain has these cavities inside. These are what are called ventricles. So inside your brain, there's these cavities depicted there in the green that contains this cerebrospinal fluid. And you have 4 cavities. You have 2 lateral cavities, indicated here, that are connected by these passages that are called the foramina Monro into a central cavity, or the third cavity, the third ventricle. And then that third ventricle is connected through this passage that is called the aqueduct of Sylvius, or the cerebral aqueduct, into another cavity in front of the cerebellum that is called the fourth ventricle. So the cerebrospinal fluid is actually secreted in those cavities. It's secreted in the ventricles. Inside the ventricles, there's a formation that is called the choroid plexus, which is a network of capillary arteries. And this network of capillary arteries, that is called the choroid plexus, from these arteries, plasma is secreted into the ventricles, and then flows from the 2 lateral ventricles into the third central ventricles, and then it flows through this aqueduct of Sylvius. Here you have between 4 and 5, into the fourth ventricles, where there's additional generation of cerebrospinal fluid. And then it flows through this hole here that is called the median aperture. It flows into this blue space that is called the subarachnoid space. It's a space between the brain and the arachnoid membrane. So then it circulates down through the spinal canal, which is not depicted here. So it goes away from the foramen magnum, which is the opening to the canal, all the way down to your sacrum, and then goes back, and then circulates around the brain in this subarachnoid space, and then is filtered back into the veins that surround your brain in what is called the arachnoid villas, just indicated here. So there you have already something very important, because it's secreted in the ventricles and is reabsorbed in the periphery, in the arachnoid villas. It has to circulate. So those of you that study fluid mechanics, you know if the sink is not collocated with the source, right? The flow has to go from the sink to the source. So we know that it has to circulate, right? So this is how your brain maintains a constant pressure, because the secretion of this cerebrospinal fluid is regulated by osmotic pressure differences. So this choroid plexus, that, as I explained before, is this network of small microcapillary arteries, are surrounded by this group of cells that are called ependymal cells. And these cells secrete ions, primarily calcium and sodium and potassium ions, and create what you know as an osmotic pressure difference between the artery and the ventricle. So it draws water from the arteries into the ventricles. So this process is actually a constant process which is only regulated by these cells. And your brain secretes about 0.3 milliliters of this cerebrospinal fluid per minute, every minute of your life. And that is independent of the pressure you have inside your cranial vault, because it's osmotically driven. But the reabsorption up there in the arytenoid violets have these little membranes that if the pressure increases in the cerebrospinal fluid, then fluid is filtered across the membrane. So the filtering is, the absorption is proportional to the pressure. And that's how your body maintains constant intracranial pressure. Because imagine if this is the steady state pressure, right? If the amount of cerebrospinal fluid increases in your brain, the pressure increases, absorption increases, and then you return back to the stable point. Consequently, if the amount of cerebrospinal fluid decreases, the pressure decreases, absorption decreases, you return. This is what you call a stable point. And that's how all of us sitting here, we have a mean intracranial pressure that is constant, while this fluid is constantly secreted and absorbed. There's a case that probably most of you, or those of you who have babies, are familiar, which is called infant hydrocephalus. It's when this process is deregulated. Is when the babies are born with this arachnoid pilus totally or fully formed, and then they secrete more cerebrospinal fluid that is reabsorbed. And then what happens? The pressure in the crane increases, and because the skull of the babies are not fully fused, right, the head of the baby continues to enlarge. And those of you who have babies, you probably remember when you took them to the pediatrician, every 3-4 months they measure the perimeter of the head to make sure that this effect is not happening. Right? But that happens only in babies. In any adult, this is already formed in all of us. So at any given time, all of you guys there and me, we have about 150 milliliters of cerebrospinal fluid inside our system. Of that, about 30 milliliters are in these 4 ventricles. 70 to 80 milliliters are in what we call the subarachnoid space surrounding the brain, and 40 to 60 is along the spinal canal, in this subarachnoid space that separates the dura membrane from the nerve, from the spinal nerve, right? And this is a very important thing that I would like you to remember, that at any given time, there's about 50 to 60 milliliters in the spinal canal, right? Well, the first thing that you see is if you generate about 140 to 170 milliliters per second, milliliters per minute, then this fluid has to be replenished 4 to 5 times a day, right? So inside our central nervous system, this fluid that is secreted from the arteries and is reabsorbed in the brain is replaced 4 to 5 times a day, right? And that's the process that then brings the nutrients, bring the hormones, control the electrolytes, right? And then remove the product of the metabolism in the system, right? So is, like I said, replaced 4 to 5 times. So there's another very important consideration, and I will finish here with all this introduction. Your brain is a rigid cavity, right? I have indicated that rigid cavity here in black. So this black box is your brain. That is only connected at the base of the brain to the spinal canal. It's connected through an aperture that is called the foramen magnum. And the spinal canal is a canal that is elastic canal. It has a very small elasticity, right? So you have to remember that the brain now is connected to a canal that has a small compliance, right? And the brain is irrigated with the blood that comes through 3 main arteries. The 2 carotid arteries that come along your neck, and they go into that foramen magnum behind your ears. And then another artery in the back of your neck that is called the basilar artery. But the 3 of them bring, with every heartbeat, blood inside the brain, right? And simply by a conservation of mass, so if whatever heartbeat, there is an increase in the flow flowing into the brain that produces a fluctuation in the intracranial pressure inside the canal. And that fluctuation then is accommodated by the cerebrospinal fluid flowing in and out this compliant spinal canal. And that's precisely what you see in this. So this is an MRI of a patient where you can see the pulsation inside the brain. This is the entrance to the spinal canal, and you can see the oscillation of cerebrospinal fluid. In white is the spinal cord of the nerve, and you can see the fluid surrounding that is oscillating. This is a velocity measure at the third cervical, which is roughly in the middle of your neck, and you can see that you have this oscillatory flow. But the very important thing is that the stroke volume that goes in and out of that canal is only about 2 to 4 milliliters in every stroke. So now think of this long spinal canal that is about 70 to 80 centimeters of length, and at the entrance you have this very small pulsation, periodic pulsation of fluid going in and out, right? So now the question is, what type of flow then is generated inside that canal by that small fluctuations in pressure? And it has been shown, there was a very early paper published by Giovanni Di Chiro in the 60s that was published in the Journal of Nature, and Di Chiro was the first one that did experiments with monkeys. He injected in the monkeys in the lumbar region, so somewhere around the waist in your back, he injected radioactive traces, right? And then saw that those traces were moving up along the canal and reach the brain in about 15 to 20 minutes. He also injected these radioactive traces in the ventricles, and so also that in 15 to 20 minutes, they were observed back down in the sacrum. Later on, there was many other experiments, and for instance, Graves and Hannett had repeated this in humans and observed the same effect. So that simple observation led to all the physiology books to put this picture that said, well, the fluid is secreted in the ventricles, it goes through all these various apertures, and then goes into the canal, and then goes all the way down to the sacral region, and then return all the way up. And that's, if you pick up any physiology book today, you're going to see that that's the picture that is shown in there, simply because this observation from Giovanni Di Chiro and led into the other observations. But the question is, how is that flow established? How is established the motion of this cerebrospinal fluid along the length of the spinal canal and return to the cranial bulk? And the question that we have been interested is, can these periodic pressure pulsations in the cranial cavity induce this bulk recirculation motion? And if it is, we want to know what are the characteristics, because this is what is very relevant. It's very relevant because we know that the absence of that circulation may compromise the normal physiology of the brain, of the central nervous system. And we also know that this bulk motion in the spinal canal determines the location and the concentration of this chemotherapy that is injected in there. Right? All right, so that's the first problem that I would like to discuss with you, the circulation of the cerebrospinal fluid in that canal. En español diríamos el circulatorio del líquido cefalorraquídeo en el canal raquídeo. Right? So the first consideration is that this is the actual anatomy of the canal. Notice how slender it is. Right? This is an MRI CAT of the canal. This is actually of one of my graduate students. He's a 24-year-old woman in perfect health. And you can see the first thing that strikes your attention when we reconstruct this is that the canal is very slender, right? And there is a very small gap between the dura membrane and the nerve, right? The spinal nerve, where this fluid is contained. So that's already tell us some clues of how we can formulate this problem. The next important clue is that we know, first of all, what I mentioned before, that the canal is very slender, so that the length, which is about 70 to 80 centimeters, is much greater than the perimeter of any cross-section, and much greater than HC is called the width, or the gap between the nerve and the dura membrane. And that is simply, if you write the conservation this, something, when I translate that to your computer, this should be much greater than this, much greater than that, and much greater than that. So what you see is that the flow is dominated basically by the axial component of the velocity, right? And has a small azimuthal component of velocity and a small radial component of velocity. I hope these equations are not all screwed up after this. Well, they are, okay? I should not blame it on them. I checked it and I didn't realize it. Okay, but I'll help you with this. So the first thing that you know is this stroke length, the stroke volume that goes into the canal divided by the total volume, that we're going to call this quantity epsilon. This is a quantity that is of the order of the stroke length that you have of this oscillation of velocity divided by the total length, and that's a very small parameter. And it gives you characteristics velocity that are of the order of this small parameter times the frequency of that pulsation, which is roughly your heartbeat, the frequency of your heart, roughly 1 hertz, times the characteristic length of the canal, right? So if you write the momentum conservation equation, the first thing that you see is because of this small parameter, this second term that we call the non-linear inertia term, this second term is very small compared to the acceleration term, of the order of epsilon to the -1, right? Remember, epsilon is that ratio between the stroke volume and the total volume that we say that is 1/50th or 1/60th, right? So that's the first thing that you say, that when you formulate the problem, in the first order approximation, this nonlinear term can be neglected. So if you look at the leading order solution of this problem, you're going to see the problem is a linear problem, because that nonlinear term doesn't contribute. The next thing that you see is that then the flow is dominated by the balance between viscosity and inertia, and the ratio between the two is what is called the Wormsley number, which is of the order 1. This squared should be of the order 1. This Wormsley number, probably some of you have seen it referred as the Stokes number. So actually, alpha squared is the Stokes number. So the first thing that this gives us is a clue of how we can formulate the problem. So I'm going to go very quickly to the equation. I know you don't want to be bothered with many equations, but just simply say that we then calculate the Aurelian velocity field by formulating the problems in dimensionless quantities. We have the continuity equation and the momentum conservation equation, where, again, with this dimensionless coordinate, you would see that the nonlinear term has a factor epsilon in front. So in a first order approximation, this term is very small. And the next thing that I have to say is that we solve the flow structure interaction. So the canal is assumed to be an elastic canal, and this H prime is the variation in the width of the canal as a function of the pressure, where K will be an equivalent constant of elasticity to that canal. So you have to think that when you put a pressure fluctuation in the brain, there is an elastic wave that propagates down the canal, because the canal is elastic, right? So then we seek for solutions for epsilon less than 1, so we do an asymptotic analysis where we expand both the velocity u, v, and w in power series of epsilon, as well as the pressure, and then we solve this asymptotic problem. So the leading order oscillatory motion is that where, you remember, the nonlinear term is negligible, so the problem reduces to a linear and a steady lubrication problem. It's actually very simple. If the fluctuation in pressure in the brain is assumed to be a simple sinusoidal cosine of omega t, you can even get analytical solutions for this. And what you see then is that this fluctuating velocity that you generate at the foramen magnum is of the order of 1 or 2 centimeters per second. And as you go down along the spinal canal, the amplitude of fluctuation decreases until eventually becomes 0. So the zero order solution is essentially that linear problem. But if you look at a fluid particle, right, that first order solution make a fluid particle simply go up and down, up and down, up and down, right? There's no bulk motion that corresponds to that leading order solution, correct? It's a total linear problem. Now, if we look for the next order solution, the first order solution, now we collect terms of voltage epsilon, taken average over one period, and then what we obtain is what is called the steady streaming component. Essentially, is the contribution of this small nonlinear term that actually makes that after fluctuation, the particle actually doesn't return to the original point, but actually there is what we call a steady streaming component that gives this component of velocity, and when you do the analysis, you see that that velocity is of the order of 1 centimeter per minute, as opposed to 1 centimeter per second. So 2 orders of magnitude slower. So the total Eulerian velocity field then is given by this leading order oscillation, which is velocities of the order of 1 centimeter per second, and then this correction that we call the steady streaming with velocities of 1 centimeter per minute. But that's not all that is happening in the problem. If you want to look at the Lagrangian transport of the particle, and again, I apologize that when I gave my presentation to your computer, all the minus and all these signs have been replaced by this box. But basically, what this tells you is the following. Because there is a gradient of this leading order velocity, u naught, as you move with x, when a particle moves in this fluctuation, move from a point where the velocity u naught actually decreases, right? So when we return, right, there is a drift, this is what we call the Stokes drift, and in average, there's what we call a drift velocity. And this is something that you have seen very much, for example, in surface waves. And there's a movie that should work, but again, in the transformation didn't work, that you will see that if there is a wave propagating from left to right, those dots, blue dots, as the wave goes by, will undergo a periodic circular motion, but it will not return to the original position and will continue drifting. It will continue drifting because we'll encounter a gradient of that velocity, u component of the velocity, with depth. So this is a very similar effect. Right, so taking all of that into consideration, then we can compute the time average Lagrangian motion of this particle, which is the sum of that steady streaming and the Stokes drift. Remember, this is of the order of centimeters per minute. So we have actually applied this to a simplified canonical case, where essentially we solve all these complicated equations for a very simple geometry of the brain and the spinal canal. We simulate the brain as this rigid cavity, where we introduce a fluctuation in pressure with a small amplitude delta P, and now the canal is surrounded by an elastic canal, and inside I have a rigid canal that corresponds to the spinal nerve. Right? The canal is closed at one end. So this is the simplest model that you can think of that spinal canal. And what we see is that we will expect that this axial component of the time average Lagrangian velocity generates a flow. Let's go back. Generate a flow which brings fluid upwards in the narrow region, we put an eccentricity in the canal, and downwards into. So there you have an explanation of that motion that has been for many, many years, more than 50 years accepted, but never explained, of that bulk recirculation motion. And what we found is depend very much on the elasticity of the canal as well as on the geometry. Right? This is just to show the simple geometry. We can do that with the actual geometry of the canal. And these are the three components of the velocities, where you can see that this time average Lagrangian velocity, right, brings fluid upwards through the narrow region, upwards to the narrow region and downwards through the wider region. And the amplitude of the velocity of that UV decreases as you go down. Okay? We have done also simple experiments to do or simulate what Giovanni Di Chiro did by putting these radioactive traces. So what we can do is to inject at a certain point something in our case is fluorescent, and see what is the Lagrangian transport of that, and see if it corresponds to our models. And again, this is a movie that didn't work when I put it, but these are the time frames of the movie. And you can see clearly what we were expecting, right? That over time, and this is from 0 to 900 seconds, if you inject a bolus of fluid, you're going to see the transport upward through the narrow region and downward through the wider region, created that recirculation. And when we measure, we see that indeed is of the order of centimeters per minute, so it's 2 orders of magnitude larger than that. To finish this part, so this is the take-home message that I would like you to take home with, and is that we have for the first time explained how is the motion of this cerebrospinal fluid in the central canal, and demonstrated that is the result of these two effects, this steady streaming Eulerian velocity, and also this nonlinear, which is associated with the nonlinear inertia, and this Stokes drift, which is associated with the non-uniformity of the leading order solution. And we have shown that this correspondingly typical dispersion times of the order of 20 to 30 minutes, anything that we inject in the canal, right? So now what we're working is with anatomically correct models where we can now provide the doctors with methods in which they can optimize the amount of chemotherapy by knowing what is the rate at which this chemotherapy will be absorbed in the tissue. The model is a bit more complicated that I explained because you have to also include the absorption of the drug in the tissue. It had also to include the decay and the possible dispersion due to other effects such as, for example, diffusivity, although the molecular diffusivity of all these molecules is very small. All right, so now let me move to the second problem that I want to discuss for you, also related to this cerebrospinal fluid, is what is called idiopathic normal pressure hydrocephalus. Idiopathic is this fancy word that the doctor said when they don't know what causes. If they don't know what causes it, is idiopathic, okay? En español le llamaríamos hidrocefalia normotensa idiopática. Now you see why I didn't want to translate all into Spanish, because the translation is not that obvious, okay? But this is how it's called. And idiopatica is the same thing. It's because we don't know why this happened, okay? This is something that was observed in the 60s by a very interesting and very successful researcher. His name was Hakim. And Hakim observed that in some patients, for reasons not well understood, the volume of cerebrospinal in the ventricles suddenly increased to a huge amount. And by huge, I mean the volume of cerebrospinal fluid there could be 10 times the original volume. What that means is that the brain parenchyma is being compressed by this fluid. Consequences, when the brain parenchyma is compressed, the brain function is impaired. And these patients were first observed because as the brain parenchyma is being compressed by this cerebrospinal fluid, then they develop certain signs. The first sign is urinary incontinence. Right? The second sign is disturbed gait. So they begin to walk with opening their stand, and they get sort of stuck in their stand. So that's another typical. And the third, more important, they develop dementia. They forgot what they ate in the morning, or they forgot the name of their wife or their kids, and so on, right? So this is what is also referred as chronic adult hydrocephalus, or also Hakim disease, because Hakim was the first one that observed this. And it is extremely underdiagnosed, because look, all these symptoms that I've been describing to you, if you have grandparents or great-grandparents, probably would say, well, they all have some sort of this, right? So approximately we believe that 12 to 15% of all the individuals that are in the assisted living or extensive care have this condition. This condition, remember, occurred when it's called communicating because there's no obstruction in the foramina or in the aqueduct of Sylvius. And the production is equal to absorption. So that's the question, so how can this develop when the amount of fluid that is being produced is approximately equal to the amount of fluid that is being absorbed, right? And there's no seemingly obstructions in any of these canals. And that's the question that we have been working on. So to answer that question, let me first say a few things why this is important. The way that this condition now is treated is by drilling a hole in the head of an individual and pulling a shunt and then draining through a valve this fluid back into the abdominal cavity, right? And what they found is that some individuals, few, they recover the function. So we know it's a reversible process. But in a large amount of them, they don't. Why? Because first, this disease happens over a long, long period of time. So the time for this accumulation may be months, even years. So during that time, the brain parenchyma has been compressed. So it may have actually go through atrophia. So when you now remove the fluid, you're not going to recover the function. Therefore, here is the important motivation for us. There is a need to develop an early diagnosis of this disease. Because if we catch this thing early, then by doing this drainage, we can recover the function, hopefully. Okay? Oh, what happened? Oh, all right. All right, so recall what I said before, okay? So that you have this fluctuations in pressure in the cranial vault. This fluctuation of pressure is not going to cause only fluid going in and out the spinal canal, but also causes the cerebrospinal fluid to go in and out. This should be a movie, and this should be a movie. So it causes cerebrospinal fluid moving in and out the cerebral aqueduct into the brain. In other words, I apologize because the movies again is not showing. It will show that with each heartbeat, the ventricles of the brain are expanding and contracting, expanding and contracting. And we can see that because we can measure that flow in the cerebral aqueduct and measure the stroke volume. We can measure how much volume goes in and out of the ventricles. So we know how much expansion happens in the ventricle. And that's a very important consideration. With every heartbeat, your ventricles are expanding and contracting, expanding and contracting. We have been observing that also with measurements, and the amount that the volume expansion and contraction can be 10 to 20%. So it's a large amount, right? So if the ventricles are expanding and contracting, that means that the pressure inside the ventricles is larger than the pressure outside in the subarachnoid space, right? And we can calculate that. You guys know fluid mechanics, and you know simply if you formulate the conservation of linear momentum along the spinal canal. So if you can measure with MRI the velocity variation as a function of time, and the components of the velocity in any cross-section, you can calculate the gradient of pressure. So you can calculate how much pressure difference is between the vein ventricles and the median aperture, and since the motion of the fluid in the subarachnoid space is very, very slow, so you can assume that you have constant pressure. So you can measure what we call the transmontal pressure. So now we know how much pressure is being put in the brain with every heartbeat as the brain ventricles are expanding and contracting. So the next important observation is the brain is a viscoelastic material. For those students, you remember what a viscoelastic material is, right? So it's a material that, imagine that you have this material indicated here in blue. If I applied a stress, a force per unit area, and produce a strain, epsilon, if I applied a constant stress, and then I remove the stress, a viscoelastic material developed first an elastic deformation, followed by creep. So while the stress is constant, the material keeps deforming. And then when you remove the stress, you recover an elastic stress, and then you have a recovery time. And the recovery time depends on the amplitude of that stress and then also depends on the elasticity and the viscosity of the material. In other words, if the brain is a portal elastic material, it depends on the elasticity of the brain and the permeability. So the recovery time, which is this time, is proportional to, inversely proportional to the elasticity, the stiffness. So the stiffer it is, the faster it recovers, right? And then proportional to mu, which is the inverse of the permeability. The less permeable, the longer will take fluid to come in and recover the shape, right? So that's a very important observation. So our theory then is the following. Imagine that you have a brain where the elasticity and the porosity is such that with every heartbeat, and now you see that the brain parenchyma is compressed and expand, right? The recovery time is such that is shorter than the period. So the brain is compressing and expanding, nothing happened. But now if with age or with certain disease, either the viscosity, right, the brain elasticity, or the permeability, or this transmural pressure that I mentioned increase, then what you're going to see is the recovery time becomes larger than the pressure, the period of the pressure fluctuation, and you're going to have what we call a residual strain. And that residual strain will make the ventricles continue to larger and larger, where all the mean intracranial pressure is the same, right? Now you may have to say, well, but how is this possible if we say that production and absorption is the same? Well, because it happens over a very long period of time. We know that this happens over years. So let's be conservative. Let's say that this idiopathic normal patient hydrocephalus has occurred in 6 months. 6 months is 15 million heartbeats. 15 million times that you're doing that. So even if you have a residual strain of 100 of a micron, over 6 months will give you a residual strain, an enlargement of the brain of 1.5. In a year will be 3 centimeters. All right, so what do we know about the elasticity, the viscoelastic properties of the brain? So that's the next thing that we did. We measured the viscoelastic property of the brain, and we do it by using magnetic resonance elastography. It's a technique that what we do is to send shear waves through the brain, and then measure the speed of propagation of the shear waves as well as the attenuation, and from there we obtain the viscoelastic properties. How we produce these shear waves? Either we gave the patient a mouth bite that vibrates, or we put it on a pillow that vibrates or oscillates, and with that we introduce shear waves in the 3 corresponding directions. After you obtain what we call the elastograms, then you have to model that viscoelastic property, and what we see that the best model is what is called a spring pod model. Here what we are showing is that when we compute the shear model of elasticity, the 2 components, and you know that's a complex number, when you compute the real and imaginary power part, we see that this model fits better the experiment. Let me explain what this model is, what may not be, most of you may not be familiar with. It's a model that is formulated in fractional calculus, so that says that the strain is proportional to the derivative of order alpha of the strain with respect to time, where alpha is a quantity between 0 and 1. Sigma is the stress, eta is the viscosity that in our case is very similar to water, and epsilon is the strain. So what we do is to model this with our experiment, with an MRI experiment, model the parameter K and alpha, which is frequency dependent. Notice what the model says. If alpha is equal to 0, this corresponds to a spring of a constant mu. And if alpha is equal to 1, it corresponds to a dust pod with viscosity eta. So for the rest of the talk, remember, mu then is the elasticity, and alpha then reflects the porosity or the permeability of the material. What did we find? We find that the brain of an individual is constantly getting softer. So all of you, if you are in the 20s, you have a viscoelastic modulus of viscoelastic of the order of 2.5 kilopascals. If you are 80, you have about 1.5. So as we age, our brain is getting liquefied, it's getting softer and softer. Mu decreases. However, alpha remains practically constant. Good news for you ladies, it gets much, much softer in men than in women, approximately by 10%. So you have stiffer brains than we do. Must be for some reason. All right, so what about these patients with normal pressure hydrocephalus? What we measured is that the patients with normal pressure hydrocephalus, mu decreases by a huge amount, 25%. And this permeability decreases by about 9%. Right? So we have also done measurements by looking at the specific parts of the brain. And what is very important is your brain as a whole doesn't get softer, but the periventricular white matter, so the white matter that's around the ventricles, so the part of the brain that's around the ventricles, that's the one that gets stiffer, that gets softer. It's what is called the periventricular white matter, and gets softer by 25%. Right? So now with all this measurement, we can check our theory. We can prove the concept if indeed this hypothesis for idiopathic normal pressure, this accumulation of a strain that occurs because the brain is getting softer, right, or less permeable, could be a reason. We have done first a very simple experiment where we simulate the transmantle pressure with the pressure that we have measured, that's the pressure that we measure in the patients, and with the model of the viscoelastic property both for the white matter and the gray matter. And for simplicity, we have assumed a spherical geometry, and this will be correspondent to the aqueduct of Silvius, the spinal aqueduct. And indeed, what we see is consistent with our hypothesis that there's accumulation of a strain the moment that the brain becomes softer. Even 5% will induce that. I have to say something with honesty. What? Can you guys hear me? Okay, I have to say something very, very honestly. We are not proving the theory. What we are proving is that our theory is consistent with what we are measuring. We're still very far from proving that indeed that's the case. Oh, thank you. All right, so then we have done, since we have the viscoelastic properties of the various portions of the brain, we have done a finite element analysis, taking into account, the transmural pressure that we measure, as well as its properties. And indeed, what we show is that, yes, we can prove that this accumulation of a strain leads to normal pressure hydrocephalus. All right, so the take-home message here is that we have shown that consistent with the observations that this strain accumulation hypothesis due to the brain getting softer could be an explanation for this. Okay? Again, I repeat, one has to be honest. We are not proving, we're simply showing our hypothesis is consistent. We're still far from proving. Why we're hard from proving? Because the important question now is that every medical doctor that I gave a talk, I just gave a talk in Vancouver, Canada, in the American Society of Neuroradiologists. And the first question they ask is, why? But why is the brain get softer? What biochemical processes, what protein composition, what happens in the brain to get softer? Because if we don't know that, then we don't have a way to test the patient. So what we need to understand now is what are the specific biochemical changes and protein composition or cellular structure that makes the brain get softer. Because if we identify that, then we can have then markers that can be extracted. We can do a tap from the spinal fluid from the canal and then check for all these proteins and see if indeed this patient is in this condition or not. The other important thing is what are the physiological parameters, cardiac rate, or even high blood pressure or breathing disorders that may accelerate this accumulation of the strain. All right, so to finish, I hope that I have shown you how fluid mechanics and how physics today are advancing physiology and medicine. I've shown you two examples. One is the administration of chemotherapy to to people with brain cancer. Also, this drug delivery method is also used for chronic pain in cancer patients to treat them. The reason is when you inject, let's say, the painkiller systemically in the bloodstream, only a very small percentage of that actually goes to the brain. The rest is absorbed by all the tissues. So here you can reduce, by injecting directly into the cerebrospinal fluid, you can reduce the doses by 500 times with the same effect. So that's why, and knowing this motion of the fluid allows you then to optimize the rate at which you should inject. And then the second problem is normal pressure hydrocephalus is the one that actually I'm really very fascinated with because, as I said before, is potentially the only reversible form of dementia. As age population of elderly people increases, we're going to have more and more parents, grandparents, or even ourselves in a few years that we're going to be exposed to this, okay? And it's very important. All right, so that's what I would like to do, and I would like to acknowledge the contribution to one of my colleagues, Antonio Sanchez, known probably to some of you, definitely Abraham, you know him. He's a very gifted individual that actually was the one who came with the idea of using this asymptotic perturbation analysis to study this. Carlos Martinez was one of my former graduate students. He is now the president of the University of Jaén in southern Spain. Victor Houghton is probably the world leading neuroradiologist, which introduced me to the problem, and I worked closely with him. All those patients that you saw, all these MRIs are from his patients. Tino Paulak is one of my colleagues that has contributed. And these are the name of all my graduate students: Jenna Lawrence, Bill Coonan, Cándido Gutiérrez Montes, and Ernesto Criado Hidalgo. With this, I would like to finish, and please, if you have any questions, I would be glad to answer them, either in Spanish or English, whatever language you want to use. Thank you.
¿Hay alguna pregunta?
¿Alguna pregunta?
Sí, adelante.
Hay mucha variación en la velocidad.
He's asking a very important question. He's asking, let's go back to this result. Okay, I'm getting there. Here. So this is this canonical case that we have, and shown that geometry is very important, that eccentricity is very important. Okay. So what he's asking is, in an actual patient with a different anatomy, will this bulk reciprocation motion depend? And the answer is yes. It depends very much on the anatomy and depends very much also on the physiology, the amplitude of that pulsation of pressure. So what we're doing now is patient-specific studies. But what we're doing is obtain this information that I showed before for each patient and have the reconstruction, this one, right? And that's the anatomy that we introduce in our model. Remember, we use this curvilinear coordinate, so S is the azimuthal coordinate, X is the axial coordinate, and then Y is the radial coordinate. And this is the actual geometry. And your question is very much to the point, because look what happens in this particular patient, that the spinal canal is open here, most likely more in the back, right? And then here, it changes from back to front, right? And we see that every time that eccentricity changes, it leads to a very important effect. It leads to actual formation of cells where the fluid gets trapped. Right? So that's a very important effect. Yes.
Sometimes the spinal canal is reduced, so the people have incontinence and lost the sensitivity in their arms and legs. So my question is it related with the idiopathic normal pressure?
No, I think what you're referring to is trauma or problems with the spinal cord. The spinal cord that is indicated here, this is a very simplified geometry. It has in every vertebra, in between the vertebrae, they have nerves that emanate, that goes all throughout the body. And here, near the lumbar region, it finishes the canal and begins what is called the, in English, they call it something like the tail of a horse, the echina cauda. And there's all the nerves that goes to the leg. So any damage into all these nerves that goes through the vertebra, either by a bulging nerve or by degeneration of the vertebra, that's what causes, right? But the cerebrospinal fluid, no. The cerebrospinal fluid, the only thing that affects in the brain is that the brain parenchyma is compressed. And because the brain parenchyma doesn't have uniform properties, it compresses more in some areas than in others. So there are certain functions that are affected first, and then others. And that's why the first symptom is urinary incontinence, because that's the area that is compressed the most. And then is the motor skills. And then finally is the memory, right? But it's mainly a neurological function. It doesn't impair the motion. It's just the coordination of the motion.
Una última pregunta muy breve, por favor.
In the evolution of the stress, you are using a fractional derivative. So
Yes.
in the order of this derivative, is it exactly the permeability, or do you feed it, or how do you model that?
Well, very good question. That's a very good question. He's asking, what is the meaning of this dashboard model that I'm using? Let's go back to that model and you see it. Sorry that it's taking so long to go back to that slide. Okay, that's a very important question. He's referring to the way that I'm modeling the viscoelastic properties of the brain. And that I'm modeling using this string pod model that composes of an infinite number of spring and dash pods. Right? And so what I try to give you is more or less what is the physical explanation of the meaning of alpha. Because as you see, when alpha is equal to 1, it reduces to a dashpot. When alpha is equal to 0, it's purely in spring. So the interpretation then is that this alpha has to do with, let's say, the viscosity, or in other words, the permeability or the porosity of, right? So that's how we interpret this parameter. But obviously, you're correct. With this fractional calculus, it's not that simple to give that a physical meaning.
Thank you.
Bueno, ya no hay tiempo para más preguntas y le agradecemos al doctor Lasheras su presentación. Gracias.